Welcome everybody, this is Isis with today's webinar on the IEA PVPS Task 13. Please hold the line while when we begin the webinar shortly. Welcome everybody, this is Isis with today's webinar. Please hold the line and we will begin shortly. All right, welcome everybody. This is ISIS, the International Solar Energy Society, and today we are happy to present to you a webinar by the IEA PVPS Task 13 on the topic of enabling second life photovoltaics. Now I'm going to give you a quick few words into ISIS and the work we do before we start the webinar. All right, so ISIS, who are we? ISIS, the International Solar Energy Society, is a UN accredited membership NGO. We've been founded in 1954 and we are accredited with the UN since 1992. We are active all around the globe and we have individual as well as corporate members from 110 countries around the globe. And our vision is 100% renewable energy for all, used efficiently and wisely. To achieve this mission, ISIS has a range of key activities, such as our biannual congresses all around the world. One is taking place this year, that's Eurosun 2024. And then again, next year, we will be having the ISIS Solar World Congress 2025. We also produce two key publications. One is Solar Energy Journal, which is quite a prestigious and well-established journal, which started its publication in 1957. And then in 2021, we added the fully open access journal Solar Energy Advances. We also conduct webinars, as the one you're seeing today, and we have education initiatives for our young members, both online and offline. Additionally, ISIS puts out infographics on different solar topics, and just recently we launched our Solar Energy Virtual Museum. Now, before we head into the webinar, some remarks on the Q&A session. Yes, there will be a Q&A session for all of your questions, and it's going to be towards the end of the webinar once we've heard all the presentations. You can already start typing in your questions anytime throughout the webinar once they come up for you. Please keep your questions short and precise, and please indicate who the question is for. This will help us with the Q&A session. Now, it's my pleasure to introduce you to our moderator for today, which is Gernot Oreski. Gernot is going to be the moderator and also the first presenter for this webinar. Gernot is the division manager at the Polymer Competence Center in Leoben in Austria, where he heads the Sustainable Polymer Solutions division. And he's going to give us some insights into both the work of the IEA PVPS Task 13, as well as give the first presentation. So Gernot, it's my pleasure to hand over to you. One second while we share the screen.
So, hello everybody. Screen sharing on. So, today I have the honor. So, do you see my screen? I'm not sure if
yes, we can.
Right one. Do you see me or my presentation?
I see your desktop. I don't see your presentation. It's opening.
Okay, how can we fix this? Okay, I'm sorry for that. So I still don't see the presentation, I guess. So that's nice.
No worries, we'll get there.
Works, everything works fine in there. So now you see something, or?
No, hold on, let me do something else. All right, I'm going to reshare the call to share your screen. And when you accept it, please hit the little arrow that lets you select whatever you want to share. There you go.
Oh, the arrow comes up at this screen down below here. So which one do you see now?
The one with the desktop.
So it's
yeah, there we go. Okay.
There we are. Sorry
okay,
for
I
that.
can see. I can see it now. Good, thank you. Go ahead.
But do you see the presentation mode as well?
No, it's in the preview mode.
Okay. Sorry for that. I have 3 screens and technical problems because our IT is not working as it should be. No. Okay, 1 second, then I have it. So meanwhile, on behalf of Ulrike Jan, the operating agent of PVPS Task 13, I would like you to welcome to this webinar on enabling second life photovoltaics. So today, the speakers were planned to be Gabriele Eder, Laura Bruckman, and Roger French, but unfortunately, Gabriele Eder literally lost her voice. She cannot speak, and therefore I have to take over her presentation as well. So, few words about what is the IEA Photovoltaics Power System Program. So it's a program started within the International Energy Agency, which was founded in 1947, and where its member, so it's like 27 countries and 5 associations, work together on certain topics that are relevant for photovoltaics. We are all working in task 13 that is dealing with reliability and performance of PV systems. And within our work program that is like updated every few years, we work on certain topics, like this is our current work program. And the aim of the task is to collect, let's say, the state of the art, to describe novel developments in the whole world of photovoltaics, and to publish reports on these topics. And where can you find these reports? These reports are publicly available on the IEA PVPS Task 13 webpage. Here you can find the link and also all the other information on the task, on the work, and as well as these presentations you can later find on the website. So let's go into the topic. Today's topic of the webinar is enabling second life photovoltaics. What do we mean? What to do with decommissioned PV panels that are still functioning well, for example, have just decommissioned because of economic purposes, and how can we, let's say, ensure reliability and also energy yield for the future. So we have 3 speakers. The first talk will be about potential repair of PV modules with backsheets, with damaged backsheets. That is the talk of Gabriele Eder, where I will proxy. The second talk will be then Laura Bruckman. She will talk about reliability aspects of PV backsheets in general. And lastly, Roger French will talk about what is the demand on repair in general. So let's start with the first topic, which is called development of a repair methodology for PV modules with damaged backsheets. Just to give you a short introduction, why is it important? So the backsheet is usually a multi-layer polymer film on the backside of a PV module, and its main functions are the electrical isolation of the solar cells, but also mechanical protection, weathering protection, and to act as a barrier against water vapor and oxygen. And when this backsheet fails, it can have, let's say, major consequences. First and foremost, a reduced insulation resistance. This is a safety issue, but it can also cause inverter shutdowns, which then results in a power loss or in a, let's say, reduced energy yield. Other possible defects includes cracks at various layers of the backsheet, or also delaminations, or let's say discoloration of the backsheet. And let's say the issue with especially cracked backsheets is they no longer provide an effective barrier to moisture, air, or let's say other low volatile components, and that can, let's say, diffuse into a PV module. And on the longer term, this can cause corrosion of the connection, of the interconnections and bus bars. It can accelerate polymer degradation within the PV module. Further on, hotspots can be created, and overall leading to a further decrease in performance and more safety issues. So these are just some examples for backsheet failures. You see various types of cracks, delaminations, blisters, or here in the down right case, where you see this discoloration. This is because of a hotspot cell where we locally have a much higher temperature. So how do these cracks form? This is an example of one of these infamous failure cases where a so-called polyamide backsheet showed this type of cracks. And you see, depending on the climate, it takes several years for the cracks to form. In most cases, the first observation that was done was chalking, meaning when you touch the PV panels on the backside, you had a white powder on your fingers that is basically titanium dioxide, where the top polymer surface layer was eroded, and like this titanium dioxide was set free. In the next step, you saw small micro cracks forming on the surface that over time grow to really deep cracks, in most cases above the bus bars, where we have additional stresses. And in the end, these cracks were going through the whole backsheet, exposing the module interior. And you can see, like if you have hot climate zones with, let's say, more severe climatic conditions, it happens much faster than, for example, in an alpine climate like we have in Austria. And how could we possibly repair this backsheet? Yeah, we need to restore all functionalities, meaning we need to restore the barrier, we need to restore the electrical insulation, we need to fill the cracks and to provide a full deck protective coating in order to do that. So how did we do that? In a project called PVRE, we started with the investigation of the different failure modes. So we know what happened, and to identify if it's repairable or not. Then we identified suitable materials and application methods for the coating, and then we started repair trials with and without dismantling of the PV modules. And within the first project, we made a proof of concept that the restoration of our ISO, so the electrical insulation, is possible. We showed that the coatings are stable upon accelerated weathering procedures, and also we are currently still working on the natural weathering stability. So let's get a little bit more into detail. So how did we identify suitable materials? We needed to look at, let's say, the requirements, and especially what steps we need to do for a successful repair, and also what requirements we have towards the materials. So for the backsheet itself, we need a clean and water-free surface crack. The filler or the primer coating needs to have a low viscosity so that it is easy to apply and also enter the pores and the cracks and penetrates quite well. And it needs to form a water vapor barrier. And the barrier coating then needs to, let's say, fulfill all the backsheet functions like diffusion barrier, electrical insulation, and also weathering resistance. We looked into different, let's say, coating systems, one component coating systems that just cure under air or humidity, or two-component systems that cure via, for example, UV irradiation or some thermal exposure. What we needed to secure with our repair coatings is we need a good material compatibility. So our coating solution needs to have good adhesion to the polyamide surface, and we don't want any migration from the, let's say, adhesive or from the coating into the backsheet and in the other way around. So additional, let's say, requirements, especially when we repair in the field, we want to avoid solvents and dangerous substances. We need to make the coating with a brush, a roller, spray, or other means, and the curing preferably should really work under ambient conditions. Otherwise, the effort, let's say, is increasing. Next to the coatings, we also looked into application of tapes or foils with a pressure-sensitive adhesive. And here, again, also the surface must be clean, and probably we need a surface pre-treatment in order to increase adhesion. And also we need a good wettability of the adhesives. So these were the requirements. How did we then do the repair? Overall, this is the outcome of the project. And if you're interested in the whole procedure, you will see we did 2 publications on that that are open access, so you can look them up at the respective journals. So first, we did a cleaning of the surface with just a damp towel, and then waited for a few minutes in order to have a dry surface. Then we did the coating. That could be a 1 or a 2-step application for crack filling and continuous stack. And obviously, it's easier when you dismantle the module and do the process in a horizontal position, but we also did in-field repair without module dismounting. The repair materials, so we found a modified polyurethane, 2-component coatings, and flowable 1-component silicon coatings to show the best results, where we applied thicknesses between 100 and 200 microns. We also tested different tapes that we adhered. And how did we do the application? Yeah, with spray coating, with brush, or let's say very efficient is squeegee, where you can cover, let's say, larger areas quite efficiently, and with some, let's say, exercise also very consistent. Yeah, and as I already teased, we were successful. We could show that both of our coating solutions sealed the crack and also added an additional protection layer on top of the whole backsheet. So we really did the job there. We were successful, and additionally, we also could restore the wet leakage insulation of the PV module with that coating. The coating showed a great stability upon accelerated aging tests, where we did especially damp heat and thermal cycling in order to see if there are chemical changes in the coating or if it shows delaminations or mechanical failures. Currently, we have still running 2 natural or 2 test cases under, let's say, natural conditions. So we have our first repair trials in a test field that are under surveillance from 2020 on. I think next month we will do the 4-year evaluation of this repair. And a second test case, which is a small rooftop system that we installed 2021. And also here we keep on continuing monitoring it. So far, after 3 years, we didn't see much, let's say, change or damage to the repair coating or the module itself, and the energy yield is just fine. Yeah, what brings the future? We are not at the end. We currently started a follow-up project where we looked into, let's say, more repair scenarios, where we just want to temporarily restore the insulation resistant, or let's say discuss a preventive coatings for second life PV modules. And we want to open up not just going from polyamide backsheets, but also other backsheets and backsheet types with different materials, show these cracks, and want to expand, let's say, this approach to other materials. Yeah, as I said, these are the objectives for the further work. And additionally, we see that a lot of backsheet damages also, let's say, result from transport or assembly of the PV system. And also here we want to look deeper into, let's say, localized repair solutions, and especially the reliability of these repair solutions in the future. Yeah, with that, thank you. If you have questions, as told before, please post them in the chat, and we would be happy. So Gabriele Eder is present, and me, we would be happy to answer all your questions later on. And again, I'm sorry for the confusion at the beginning, and also that I'm not that fluid for the presentation because I just got it yesterday, the information that I need to hold this presentation. Okay, with that, thank you very much for your attention. Looking forward to a question, and I give over the word to Laura Bruckman. So Laura is associate professor at the Case Western Reserve University in Cleveland, Ohio, and she's working at the Solar the SDRE, the Solar Durability and Lifetime Extension Center, together with our last speaker, Roger French. Yeah, she's a material scientist working especially on the degradation of packaging materials in PV modules, let's say as a second specialty, yeah, using modern data science approaches in order to understand problems we face in reliability. So Laura, the floor is yours.
Thank you. You're seeing my screen?
Mm-hmm. Could you go to full mode?
Yep.
Yes, perfect.
Okay, so I'd like to talk about some experiences we've had with PV modules in the field. So I've had 2 projects over the course of 3 years, which we've been able to go out in the field and retrieve modules and then also do field surveys. And so that's what I'm going to cover during this talk. And so some of our students have done a fabulous job going out and being able to understand what's actually happening out in the field. So for one project, we went out in the field and we actually were able to take on 33 modules that we retrieved from different locations around the world, from 0 to 28 years of exposure. And we had different backsheet airside materials covering from the fluoropolymers to polyamide through PET. And then what we did is we took those modules, we cut them up, and we did pretty nice analysis, and several papers have come out of those. And one here, which was published in Solar Energy, if you want an in-depth analysis of what we were completed on those modules. One thing we also really started looking at is that although these modules were really insightful and we got a really good understanding of what was happening in the field, they weren't necessarily representative of every module that was happening in the field, because many of these modules that were coming back to us were because they had failed. They were given to us because people were potentially upset, they were returning them, they had identified a problem, and so we didn't get a really good representation of what was happening across many backsheets. So some observations that we saw in these modules is PVDF. Interestingly enough, we saw that they had alpha and beta phase in their crystalline phase. We were unable to identify if those were happening prior at 0 ages or if those had changes during the course of the exposure time. For PVF, we had minimal changes to yellowness index or gloss over up to 28 years of exposure. In that case, we had a module that had been stored in a shed that had never, quote, been exposed outdoors, but had definitely had thermal changes because it had been sitting in a shed. For PET, we had extensive discoloration, yellowness index, and we also had a wide range of variability in the yellowness index. For polyamide, we saw the typical things that we have discussed all over the literature: severe cracking, microcracks, high yellowness index changes, and we also had decrease in gloss with exposure time. So some observations here that we saw is for PVF, we saw some delamination. These were also modules that had been exposed in California for 28 years. We also saw mold growth on those. For PET, interestingly enough, we saw pitting in modules that were 4 years old. We also saw some modules with clear outer layer PET, so they were not filled with TiO2, and in those cases we saw microcracking. And additionally, just like I had said, we saw these backsheets of polyamide with severe cracking in between the cells, and also microcracking and also mold growth. And interestingly, also when you look at in the yellow here for polyamide modules, we saw two modules here, PA3 and PA6, who were taken at the same climate zone, so CFA, and they had similar years of exposure. These are on the measurements of yellowness index at the same exact module, just at different points all over the module. And you'll see that yellowness index is very varied over the whole course of the whole backsheet. And so what you see here is that we're having non-uniform discoloration and degradation over the scope of the module. So what you're seeing here is that they're actually having differences of degradation over the whole back of that module. So we have a spatial degradation over this particular one here. You see very varied degradation. These are mounted on concrete roofs. These two were mounted on grass in the same climate zone with longer years of exposure. So we definitely have a difference in temperature or potentially albedo. These two on concrete roofs were also potentially a higher pollution content, so there was higher NOx there, which we know attacks polyamide. So that's something to consider, is pollution in the air can also attack these polymers. And then for PET, what we see is we have, although these were also in the same climate zone, they have wide variability of their degradation and also across the whole backsheet. So they were not very closely tight. And so we have a huge variance in the behavior of those backsheets. We also later on got an additional set of retrieved backsheets. So interestingly enough, these are backsheets that had an aluminum layer and sheet in them. And we retrieved these from Taiwan, and all of these failed a dry insulation test and had been a failed module that we looked at. And so these are microscopy images of those. These were an interesting set because these were the only modules we ever saw with this aluminum layer. Additionally, we got a set of 3 retrieved modules. These were all retrieved from Florida, South Carolina region of the US. And what was interestingly enough that we saw is we saw 2 modules that we'll talk about in a bit, but they were PET type backsheets with cracking, and they were repaired modules. They were also able to pass the wet insulation resistance test after they were repaired. There was 2 polyamide backsheets that were not repaired and failed the wet insulation testing as well. So what you see here is for the polyamide test backsheets, we have these severe cracking that are longitudinal cracks that we see. And the PET backsheets that failed the wet insulation testing, there was no particular cracks that we saw. on these back sheets. And then these were the two PET back sheets that were repaired, and they were, here's a little close-up picture that you can see they were repaired right around the junction box and then down the module. This is obviously a tape that was put on, and then they were still out in the field for a while and then taken off the field after repairing. Additionally, because we knew that retrieving modules were often getting these failed modules, so we're self-selecting modules that we're taking off the field, we wanted to go out and do some field surveys and understand what is happening out in the field. So the first field survey we did was out in Maryland, and this is a picture of actually the field that we went out, and you can see the gray rock that we have here. And we noticed as soon as we did this field survey, so this is yellowness index, we're using yellowness index because it was pretty easy to go do measurements quickly, and we could do them efficiently on the backside of the module. Students could take measurements multiple places on the backside. We had already seen that there was non-uniform degradation over the space of a module individually. And what you see here is that as we go down this row of a module, we have higher yellowness index at the ends. This yellow row here is actually the bottom row. The blue row here is this top along the way. And we were able to identify that this top row here had a significantly higher yellowness index, and then also the edges. So we were starting to call this the edge effect. We also went and measured the irradiance, and what we saw here is that the irradiance was also higher at the edges. It was also higher on this blue top row. This allowed us to kind of understand that we did not have uniform stressors on our modules in the field, which made this understanding that if we were field retrieving modules, also understanding that we weren't having a good representation of all of the modules in a field. So we started picking sites across the country, looking at Köppen-Geiger's climate zones, also knowing that the Köppen-Geiger climate zones, as we had seen in some of those retrieved modules, weren't necessarily a good representation of everything that was happening as a stressor condition. We're not necessarily taking into account pollution or precipitation or irradiance quite the same way because they weren't designed for PV modules. So we started designing a field survey protocol that was focused around PV modules. And one thing we realized when talking to power plant owners, to other field surveyors, to individuals making modules, is that we didn't have really this right nomenclature that everyone was using around what was a rack, what was a row, how do we actually name when we have multiple rows on top of each other. So we've been working to develop an ASTM standard around the nomenclature of field survey. And so we designed language. So what is a rack? What is a subrow? What is a module? What is an actual row? And the students also wore video cameras around so that they could identify exactly geolocation of where they were when they took measurements. And if they accidentally messed up a measurement, they could voice record, this was a mistake in the measurement, so we could have really good data collection. Additionally, we identified a block in a field. Fields are not, unfortunately, not all square and uniform. And then how do we identify shading conditions for all of the modules? There's shading conditions that are different, and identify all of those conditions. So we went out and we used ATR, FTIR to identify backsheet type, yellowness index, gloss, and then we started with handheld Raman as well. And then we decided where to measure on the backside of each of these modules for time and to maximize the number of measurements that we could also take. And then I'll walk through some observations. So we ended up measuring 41 sites in 7 different climate zones. We ended up identifying 7 different polymers, and we ended up at a site once with glass backsheets. And 4 sites, we were able to measure multiple time points so that we got a temporal aspect. And in all, we have over 17,000 measurements, and all our data is publicly available on OSF. And we're willing to accept other individuals who want to do field survey and add to our database. One thing we saw here is that at the same site and at other multiple sites, we still see this edge effect. You can see it here outlined in these red boxes, and it continued through time. This is 4, 8, and 10 years of an exposure. We still continue to see increase in yellowness index. What you see here on this top sub row is that it actually started in year 10, tailing downwards at the edges. What we actually identified is they started photo bleaching instead of yellowing. Also on this top row, we started seeing micro cracks in that polymer. And they had started transitioning from yellowing and forming chromophores to actually photo bleaching and having micro cracks. So we had a transition and phase of degradation types and then leading towards failure. Additionally, we saw at many different sites, this is just one example, we saw around roads that there would be this same tailing up of degradation and non-uniformity. And then at certain places, we had these modules that looked very out of place. And when we looked at logbooks, that's where they would have replaced modules or shuffled modules around. So it was really nice to be able to go look at their logbooks. Additionally, when we looked at gloss, so gloss looks at the roughness of the material, we would often see that we would have significantly less gloss, so the materials would get less rough right around the junction box. And this would definitely be related to the increase of temperature around the junction box. So we had this non-uniform degradation again around the junction box. And so this allowed us to think about what are the variants that we need to start considering when we think about degradation in the field around our studies. And the idea here, one of the things we really need to consider in our fielded modules is that irradiance is definitely impacted by ground cover. So gray rock is impacting albedo. Grass seems to really decrease it. Roads are increasing degradation. And also the distance to the ground is something we started measuring for these modules. And also we started looking at how much water was sitting on the backside of the module, how much dew point was there. So I'll quickly go through. We started simulating how much irradiance was on the backside of the modules with NREL's bifacial irradiance package. And we were able to identify with some of this dose, how much dose was actually created there from albedo. And what we were actually able to see, I will point out there, is that PET does not act uniformly. So PVF and PVDF have very uniform responses in our field survey over our data. We also know they're have been manufactured by the same companies in pretty reproducible manners. PET was coming from many different manufacturers in different ways. And so I think as a community, we need to be very careful that we don't think PET is the same kind of material or any materials unless we really understand the manufacturing process. PET is a different kind of material based on its additives, how it was manufactured, and its behavior. And so that's something that we really should consider, understanding that these materials are unique and can have very unique behaviors. And so I want to thank everyone for that.
So thanks, Laura. I think you nicely showed that there is need for repair, especially when we really think of prolonging the lifetime of a PV module. Okay, next we will have Roger French. He's also from Case Western Reserve University in Cleveland. I guess sitting next office next to Laura right now. He's professor there, And yeah, he will talk about how FAIRification of data could help in order to enable a second life PV and yeah, save the data necessary for everything. So Roger, the floor is yours.
Great. Thank you. Show my screen. And so now can you see my, oh, yeah. Can you see that?
Yeah.
You can
All
see
good
my,
to go.
good. Oh, so we just saw repairing individual modules, and then we heard a discussion about surveying modules across a power plant, which is a large number of modules. But also, if we want to actually enable second life PV, then there's a question about the provenance, so the history of the modules that you'd want to sell into a second use. And so therefore, you'd be caring about what type of module, what materials are in the module, how much energy have they produced over their lifetime, and what was any O&M, did they have to be repaired, things like that. And so that's really part of this idea that we'd like to start thinking holistically about the whole cycle of life of PV power plants. What are all their environmental, economic, and energy inputs, and then across from the materials, project development, the energy generation, end of service. This is the place where if we could find second use markets for it, then we would be in good shape for using older modules in secondary places. And so what we'd like to do then is figure out what the factors are that are necessary for a robust second life PV market. How do you value a used module that's been around a long time? So I know that in the US, for example, there's a healthy market in used PV modules on eBay, and people will buy them when they want a cheap module and don't worry about it too much. What we'd really like to know is this provenance, have the history of it. And one of the real advantages in the photovoltaic industry is that since PV power plants sell electricity, they intrinsically have time series power production data for all the power plants and all therefore the modules that are out there. And that set of data, which we don't usually think about as being data, we just think of people selling electricity, but the companies who now are owning PV power plant assets care about these tremendously, because they will analyze their data, for example, to do bidding on the 1 hour and 15-minute and next day markets for electricity sales. And also they want to study the long-term performance of their PV power plants. And so it turns out that with those facts for our photovoltaics markets, and then with the recent advances in data science, deep learning, and AI technologies, so everyone has been noticing things like ChatGPT and the large language models, and other cases where large volumes of data have become available and are being used for artificial intelligence applications, that we can actually see that having the asset information of existing is one of the ways that we can actually start understanding the history of them. And this data-enabled analysis can help establish the values in a second life PV market. So let's think about the AI machine learning type of aspects of this, and how can we help accelerate a transition to having a healthy second life market. So if we want to develop AI ML for science, like photovoltaic science, we're going to be using not just the old-fashioned high-performance computing, but also distributed computing. And we really need to sort of come up with some of the ways, and we've been working on this now for a number of years, where we call our computing environment Cradle. And so therefore, what we do with robust computing environments, which companies have now established pretty largely, that we actually are at this inflection point where using some of these AI approaches can help to do things like enable a second life PV market. And so therefore, this is a real opportunity we have. So in our research center, we have nice computing resources, and we've been working with industry members for years now on exactly these areas. So we're giving a report here about what seems to be, could be easily possible in the next few years, okay? And it really is sort of a, generically, we have in PV all of that data available. The problem is that data is problematic if it's messy and things, but if you can verify it, and I'll explain what that means in a bit, then you can take data and you can get out of it the information about things you might care about. So when you change data into information, And then if you also take that, what you learned as information and make it into knowledge, and that really requires an ontology. So this is really the data analysis business that many of us are involved in different areas. But it's also that most of all for the AI applications, you can automate those analyses very easily and make them into workflows. And at this point, you can end up with knowledge repositories that you can then ask questions of and query. So you can have AI agents who, if the data was available and became knowledge, then AI agents could help you answer questions with both inductive and deductive reasoning. I'll show you how that fits together. So in our group, we have about 100,000 PV power plants where we have all the time series data for them. They're not just in the United States, they're around the whole world. I'm just showing a US picture here, but they're in different climate zones. And then for every one of these little spots, we have the full time series data. You can think of it as going into the page, okay? And so because of this, we have spatially distributed temporal data of power plants and how they generated electricity. These are from about 20 different companies, so there are lots of different companies who are asset owners here, but they're all the people who would be one of the major sources of modules that might be looking for a second life. So how do we actually keep track of things? So you might think of data on your computer as being something that causes problems and gets lost and you can't find it. But actually, when you have a good computing system, then this is what we call our Cradle Data Explorer, and we can actually have a map of all of our systems here. We can actually find them all. There's more than 100,000 of them. And then we can actually go down to any single power plant. We'll see the metadata stored here about them. Oh, so that's interesting because that would be part of what would tell us our history. And we actually have the history of the power production. So this would be a system during the day from midnight to midnight, and then over a number of years period of time. So we can actually find these, we can actually organize massive volumes of data. And when we do then, so down here, we're in Puerto Rico, and there's a set of power plants that are in a certain area here. We can get all their metadata, we can find their information. Notice that the data actually looks like it has missing gaps and other problems. This turns out to be one of the big problems in PV power plant data, that there's missingness, there's missing aspects, and this can impact tremendously how it works. But a real advance with the recent AI advances in graph neural network models mean that we can look at two different inverters here, or two different sites, and they have some missing data. Here's some data that's there, but it's obviously not correct, okay? Nowadays, when we analyze a whole fleet of thousands of systems, we can then use nearby systems to impute the missing data and improve the quality of what we have. That turns out to be very important in improving the quality of the performance loss rate, for example, that the asset owners really care about. So they're managing their assets because they're big commercial power plants, and they really care about these details. This is a benefit. The fact that this type of analysis is happening is a benefit to a second life market. These are all done with, in the case like for performance loss rate, we actually are able to study the aging, the degradation over time of a certain power plant. And we do this on thousands of power plants all at the same time. We analyze them in mass. So a total fleet analysis over here. Knowing that asset owners are doing these kinds of analyses and that this data exists and is well managed gives a real idea that you could have not just an object that you're trying to sell as a second life PV module, but that it could be an object, a set of modules that you have a full history of what happened to them over their life. Okay, for example, we'll know the weather they were exposed to, how much power they've produced, were there any hailstorms nearby, things like that. When we collect this data from our partner companies, asset owners, oftentimes it will give us the full O&M logs. So how would we know that all this data could be accessible for use in a second life determination? Well, we've been doing things like performance loss rate determination, and a real advantage is that using these what are called ST graphs, spatiotemporal graph approaches. So in this case, this is synthetic data, but it's looking at two different cases. The truth is the dashed black line, and then these are different analysis methods, and it's really this STGNN, spatiotemporal graph approach, that most closely analyzes all of the different systems in the fleet. And the ST graph model is one of the ones that uses the large volumes of information that we know AI methods really want. So there's papers down here about that. So it seems like we should be able to do all of this, right? It should just work perfectly. Well, we have taken care of the data that the companies provide us well, but many times those companies do not. As a matter of fact, for large asset owners, we've even had where we re-export the data and give it back to them when they lose it, because people seem to lose data quite a lot. So oftentimes when we're working with data, most of all when it's just the data, we spend more time locating, querying, assessing if data is fit to use than actually analyzing and learning from it. And so what we really need to do is not, oh yes, should the conversation be, do you remember where John's old EBSD results are? Oh yes, I think those are on some CSV files on that old lab computer. And maybe you didn't throw away that computer yet, but you sort of look for it, you find some old query, and it gets maybe half of what you needed. So actually, the data side of this problem is something which is not in very good shape in our PV science community or in most of the material science community, but it is an aspect that the doctors in medical care have done an awful lot about. Epidemiologists have gotten very good at studying and paying attention to large numbers and fleets of systems. So what do we do? The big important thing is that we need to take data and make it fair. And making data fair means that it can be findable, accessible, interoperable, and reusable. And these sound like a generic concept that we're not sure exactly how to do that, but it does turn out that you can take that unstructured real data, weather data, operation and maintenance logs, power production, and if you have an ontology, which is basically a dictionary of terms and relationships, then you can organize the data, storing it in what's called a JSON LD. JSON is just the language of the web, okay, the World Wide Web. And then we can make the data fair and well organized. And there's nice principles for doing this, and we're making a lot of progress. So there are a couple of papers down here about that. And so I'll sort of show you what that process is, because this is what would enable us to know the value of things. So for example, here's SolarEdge and Brookfield Renewables. These are two of the PV companies that we work with. So that raw data that comes from them, we ingest it into our computing system. We then make it fair. And when we do that, well, we actually are developing the open source tools for the community to use. They're called FAIR materials. So you can verify your data as you go. So we're enabling everyone else to do the same thing. We can also take the data sets that are public, that are accessible, allowed to be public data sets, and we share them on Open Science Framework, osf.io. There's our research center. And then finally, we can also do the modeling like I was showing for the PLR determination. So these are these workflows. And as more and more of the industry goes towards this, and the second life PV market doesn't have to be pushing anyone to do this, because the power plant owners who are growing, their financial opportunity is growing tremendously as more and more PV electricity is being used globally. It means that it's in their own interest to manage their data, learn from it, and take care of it. So what's that ontology that's going to help us make data into something different? Well, the ontology is basically, if we just have a bunch of data here, then we can make it into information. And if we can have it as information because we analyzed it, then we connect it together with relationships, it becomes knowledge. So for example, the ontology would say here that a power plant has latitude. And so FSEC is a power plant that we study, FSEC, and it has latitude of 28.39. It's in Florida in the United States. So the ontology says we're going to define the word power plant and latitude, and then the values of it. Here's the name of a power plant, and there's its latitude. So really, ontologies are just a whole set of systems of data variable types and their relationships. And when you do this, then you have object relationship pairs. And this means that not just people can understand latitude is 28.39, but computers can. So this really enables computers. And so we've been developing the materials data science ontology. We do this as an open source initiative with that package to standardize terminology across the materials domain. So PV science is one of them. And even though we don't require people to change all their own variables, we basically make it so that the computer can look up and check whether we already know your variables. So this is a real big breakthrough in knowledge management for photovoltaics. What it actually looks like is that we do have a graph which has all of the terms for example, here's the PV ontology, and here's the node for just the PV site. And these would be all the aspects of a PV site. And that will mean that we know about the backsheet that Professor Bruckman was talking about. We know about the modules, about the site, and these are all the terms that we have defined for it. We can also now check globally, because this is an open source project, and we can see that the materials data science ontology, where the PV is also being connected to in another one called the PMD core ontology. So we can check now on the internet to make sure that our terms are making sense. That means a computer could also check on the internet to make sure it understands the variables that you hand it for doing some calculations. So these are really a big advance. They come from using graphs. And so this is an example of two representations of graphs. The computer ends up processing as triples, factual triples, but this would be a graph about Albert Einstein, who was the son of Hans Albert Einstein. He was an expert in physics. He proposed, the theory of relativity was proposed by him. He was the winner of the Nobel Prize. That is where you get AI reasoning from, okay, inductive and deductive reasoning. And so that means that the same graph approach that we're used for actually power forecasting and PLR determination enables this reasoning, which would allow us to then go looking at things that way. And so we're really moving rather quickly then into, this would be an area of foundation models and graph neural network models. This is how we do the analysis of performance of systems. And then we store those results into the knowledge graph. So this combining of the ST graph for doing performance analysis and for managing knowledge means that at the end of life in a commercial power plant, all the modules have a full history that could be handed out with them, and that would help set the value of them. That would be know the history of your PV modules, track it through its lifetime. That time series data does that. And so in task 13, in another subtask, we're actually working on a report on PV data models and digital twins to help do this. So that really is an example of this AI inflection point that fair data can allow in the PV universe. And so with that, I'll see if there are questions.
So, thank you very much, Roger. There are indeed questions, and I would say we start with your questions and then we go back, if that's okay.
Mm-hmm.
So, first question to you regarding, let's say, the use of artificial intelligence, machine learning. Can you comment on the state of the art on image analysis, especially infrared and EL imaging to detect PV failures?
Mm-hmm. So that's one of the things. So there's the use of UV fluorescence measurements is something which many groups both in around the world and in Europe and in the US are working on. We have a project where we've been looking at the UV fluorescence, and it's one of those things that is a very useful at commercial power plant sites. For example, you can survey large numbers of modules, like in the studies that Professor Bruckman was discussing, and to quantify and check that an individual module might have gotten a crack and start having some degradation enhanced by cracks in it, versus other ones would be in good shape. So these kinds of screenings of modules before they would go into a second life market could be very useful. And again, those are being done. We do them again with neural network modeling in the same kind of way, and we verify the data so it becomes part of this knowledge history of every module.
Yeah, continuing with that, what other additional measures would be recommended to increase the efficiency of errors, loss detection algorithms for PV plant operations?
Mm-hmm. So what we often do is that we will study, because we have a nice big population of modules in many climate zones and from many providers and many technologies, that really is what allows us to do epidemiological studies. So think of medical studies across populations and countries and things like that. That's exactly the same thing that we tend to do with PV. And so this is the way that we can go checking. So we can look in one subset of modules in one climate zone and see if we find a phenomena, but then we can go check in a different set in a different location, different technology, and make sure that we have seen the same phenomena. So that we don't have to just believe what the AI says, but we can instead be checking it as the actual human in the loop. And so I think that that's an important thing to distinguish. Mostly people think of artificial intelligence as autonomous, where the machine, the computer, is making all the decisions and doing things. I think actually we're going to use it as an agent, a helper to us humans, to be able to analyze large volumes of data that we would struggle with analyzing, but that we would have the human in the loop, that it would say, I would ask this question of my ChatGPT type model, let's say, and it would tell me the answer to what I asked. And then it might also suggest, but have you thought about this factor or that factor? That's where the deductive reasoning of an AI agent comes in. It can be very beneficial. This is what doctors find to be very helpful in the use of AI in medicine.
So maybe one last question to you, Roger. What parts of the history of PV modules do you think could affect the value the most?
I think from what we've learned is that the period of time, which was sort of 2008 to 2014, during which polyamide was chosen as a backsheet polymer due to lower cost, those modules are ones that have been problematic in how they last compared to other materials used in backsheets. And so knowing the material used in the backsheet of modules that you're looking to buy on a second life market would be very important. It's also knowing about the bill of materials, so it's not usually a known thing, but it is something which we can learn specific things about as we go. And I believe because the major purchasers of PV modules are these large asset owners, if they actually wanted to have declared BOM for the modules they buy, I'm sure that the vendors would sell the modules with the bill of materials. So it's the question of, do you really want the data? And if so, you should ask for it. And I bet you they give it to you.
Okay. So maybe a question to Laura. The question is, if backsheet cracking caused already a microcrack on the solar cell, does it still make sense to repair the backsheet? Maybe it's also a question to Gabi and me, but
Can you repeat it? Sorry.
If backsheet cracking causes already a microcrack in the solar cell, does it still make sense to repair the backsheet?
I think we can still repair these backsheets, right? And I think we're seeing from your work and Gabby's work that we can have repair in them. And they're passing some of these testing. And I think it's important if we're thinking about lifetime, especially second life, if there still can be qualified that the whole technology is still producing electricity, that's a good idea.
There's another question that I'm not popping in. Let's say it's more a statement. Maybe we can discuss this. A module with double glass do not present these drawbacks. They are more resistant and the useful life is longer. The future trend will be double glass, or the industry is working on backsheet materials to prevent fires, with better insulation, better environment protection. It's more than a statement. I don't know. Maybe Roger and Laura, do you agree with that? That the future will be exclusively double glass and there are no issues with double glass, or we will see even a significant share of glass backsheet modules?
So I know that in a study that we did, we directly compared for PERC module technologies, both double glass and glass backsheet. And oftentimes it's been said on the basic physics of the structure of a double glass module that cell cracking would be less of a problem in double glass compared to glass polymer backsheet modules. But that's not actually what we found, that correctly designed glass polymer backsheet modules can be as robust for avoiding cell cracking as double glass ones. And so then there's always the installer's perspective, which is that double glass modules, if they weigh more, make installations harder. And then the cost aspects of it are always up in the air. So I'm not sure that it comes down strongly on just the side of double glass modules.
And my concern too is the being able to get glass has been sometimes a problem. Is we've had a glass shortage. So we haven't necessarily had the same polymer shortage, except for when we switched from fluoropolymers to polyamide. We might still have the same shortage in fluoropolymers now with the PFAS situation. So that is also a concern. So we might be still focusing on PET type backsheets going forward. I'd like to, go ahead, Gernot.
And maybe we will see this split for residential PV. We will see more glass backsheet because of ease to installation on roofs and so, and for, let's say, huge plants, we will see predominantly double glass. Could be a potential future. Yeah, Laura, you wanted to add something?
Yeah, I was going to comment on your first question too. I don't necessarily think that cracked backsheets relate to cracked cells either.
Yeah.
So repairing cracked backsheets hasn't necessarily been related to cell problems.
Okay, there have been 2 or 3 quick questions on the repair strategy. So first one, what materials did you use for your coating solution? So one time was a silicone material provided by Dow Silicones, and it's available on the market. The second one is a 2-component polyurethane coating by Kansai Helios. You will find, I think, the information in the papers. And if you really want to know, please contact me. I can send you, let's say, the link to these materials. Both of them are now commercially available for backsheet repair. Second short questions. Are all these cracks occurred because of thermal stress or some mechanical means? It's thermomechanical stress. So we have internal stresses over the ribbons where these cracks formed. We have the, let's say, day-night expansion, contraction of the PV modules, and the coefficient of thermal expansion mismatches, and all of that contribute to crack growing in the backsheet. It was not a singular mechanical load like a snow load or wind load or something like this. And there was another. What are safety issues? I think safety issues is when we fail the wet leakage insulation test. That's the biggest safety issue that we can have when a backsheet fails. And what is this question? I think that is what Roger already answered a little bit. While bill of materials is variable for any given manufacturing line, has anyone attempted to compile a list or spreadsheet showing which backsheet materials are used for particular manufacturers and part numbers? No, I think that's just too extensive and too much, and there are too many manufacturers out there.
I don't think that's actually too much data, because we can handle large volumes. The computers can handle large volumes of data, and don't forget that
collecting the data.
The manufacturers take 2 EL images of every module they manufacture. Every module has a unique serial number, and so therefore the information exists. As long as it's already being made, all that we're asking would be access to it.
Yeah, I guess that's the biggest issue.
So in our retrieve module part, we had the same module number, and we had basically 4 different backsheets on them. But when we did field surveys, we never had a field where the modules were so randomly backsheeted. So it's definitely in commercial power plants that they're getting them in bulk, and they're pretty consistent unless they replace them. So where we did find like backsheets having non-uniform, material types is when they had gone through and replaced them, or when they had bought different lots and put them in. So for the most part, our back sheets were all consistent, except for when they installed them in a way where they hadn't purchased as a bulk unit. So for most of our 41 sites we looked at least along the strings, most of the time, they had been consistent.
Okay, there are 3 more questions that popped up now. First one is economic question to the repair. So what is your opinion regarding economic cost of repair versus cost of exchanging and buying new modules? Yeah, I would say it rather depends. So in most cases, probably new modules would be cheaper than the repair because it's rather labor intensive right now as we have the solutions, because it's right now done manually. When you have some sort of collection of decommissioned modules that you want to sell, then maybe you can think about automated coding, and that could be feasible. Feasible right now, it's for short-term repairs. And for example, we had the case repair of a PV system on top of a mountain at 3,000 meters or so, where the dismantling would be much more effort. You need to bring in a helicopter and stuff. So there the repair is actually feasible. Then there was a question to Laura still. Should we be concerned about the double-phase PV models? I mean, I think the
bifacial
PV models degradation as a sustainable solution.
So we didn't necessarily look at bifacial modules in our project, but the rear side irradiance modeling that we did would be an indicator to look at what the backside is looking at. So we do know that they're going to get non-uniform degradation or non-uniform albedo on the backside. I don't know what that's going to do to the cells, but we know we already get shading on the front side of cells, right? So it'd be a similar kind of concept that they're going to get this non-uniform, but I don't think it would be as harsh as shading, right? So it's kind of a gradual look. And I think that polymers are significantly more sensitive. We might see it in the encapsulants.
So one more question for Roger regarding the need to improve the quality of data collected across many different sites. How much of the problem is software related versus hardware related versus logistical in nature? That's a good question.
Yeah, for example, in the PV time series data from power plants, that is the one which might be due to mostly one is the reliability of internet connections, the way that data flows. And so that's one part of it. The other one is glitches from inverters or other equipment along the way that need to be reset. And but those issues are becoming ones that can be addressed during analysis, because when we do analysis, we always assess how much noise is there in a particular system's data versus how much information is there. And so you can do that. You don't have to just qualify data and say, I'm not going to use this one because I don't like it, how it looks. I'm going to use that one. Cherry picking data might be more problematic by humans than actually using statistical analysis and information theory to look at the quality of the information. We assess information entropy, which would be the amount of randomness in the noise that's of some data. And that's how we're doing these assessments of what would be the most likely imputed data when the data was missing. So methods are being developed for these things that are not the traditional ones that a person does if they're analyzing results of an experiment they did in their lab.
Okay, meanwhile, Gabriele Eder wrote that she never observed any micro cracks in cells on modules with cracked backsheets. So there is, at least so far, we don't see any connection between. And maybe the last question into the whole panel, what would be a fair price for second life PV modules compared to new ones or to the initial price, and what are criteria to consider while the remaining lifetime is uncertain?
So I think that if one were to look at the idea that the power maintenance warranty that most modules have is a 20% drop in nameplate power from day one to either 20 or 25 years in. So therefore, if you know the nameplate of a module and it has been in the field and it's at 90% of nameplate power, maybe you would say it's got half its lifetime left. And then you could look at the price of a current module per watt and price the halfway through its life module's price. But also, in many cases, people who have power plants that are already installed and they're already generating electricity, I've never heard of any of them actually taking down their power plant and turning it off when it hits 80%. Because if you already have a paid for asset that makes electricity every day and has no operating cost for you, you might be willing to let it drift down to half of its initial power output. So the market pricing needs to be established, and that's where data plays a big role if it is available on establishing a solid pricing.
Maybe just one thing, I heard in Germany there's quite, let's say, a lively second life and used module market because of the legal situation. Because when you have, let's say, long-term contracts for feed-in tariffs, you cannot change anything at the system. And when you have some, let's say, damaged modules because of hail or whatever, you can just exchange it with the exact same power, like the same power of the module. And so for certain module types, actually people pay higher prices than for new modules just because they can just put them into this very old feed-in tariffs contracts. But this is a thing that I guess will fade out in the next years as well. Okay, I think we are more or less through all the questions that I've seen. Thank you very much, both of you, for joining this discussion, and also to all of you out there to listening to the webinar. So please take a look at the PVPS website. You will find a lot of interesting reports. And if you have further questions or are interested in the topic, please feel free to contact anybody of us in the future. With that, also thanks from our side to ISIS and to Arabella for hosting us. And yeah, I give the last word to Arabella.
Yes, thank you very much to the speakers and to you, Gernot, for taking us through the Q&A and for jumping in last minute on that first presentation. Just quickly before we close out the webinar, there are a few more informations I'd like to share. The first one is that yes, there will be a recording of the webinar, and yes, also the presentations will be made available to our attendees, and that's going to be via the ISIS homepage as well as the IEA PVPS Task 13 homepage in a few days. For any ISIS members on our call, please remember you have unlimited access to all of our webinars via the ISIS members area, which you can find on the homepage. Second to last, I'd like to draw your attention to one of our upcoming conferences, and that is Eurosun 2024, the ISIS and IEA SHC International Conference on Sustainable and Solar Energy for Buildings and Industry. This year, we are going to take Eurosun to Cyprus. It's going to be in the last week of August. We just closed out the call for papers. We are in the review process, and registration for Eurosun will be open very shortly. So keep an eye on Eurosun. You can find more information on the homepage. That's eurosun2024.org. And we're looking forward to seeing many of you in Cyprus in August. And then finally, it's not always about looking forward. It's also sometimes about looking back. And ISIS has recently launched a new initiative. That's the ISIS Online Solar Energy Museum. It's a fully virtual museum where you can take a walk through 60 plus years of solar history. And we are covering all kinds of solar history and technology development throughout 6 different galleries. And so we very much invite you to enjoy that museum. You can access it via the ISIS homepage. And you can take a stroll. You can have a look at our 3D modules, which are placed all throughout. There's a big 60 plus year timeline on all things relevant to solar development. All right, with that, once again, thank you very much for joining us. Stay in touch, and we are looking forward to meeting you on the next webinar. Bye, everybody.
Bye.
Thank you.
Bye-bye.